Lecture number 7 about reflection. So we have 8 lectures in total. This is the one before the last one. And we're moving from the simplest things to discuss in object-oriented programming to more and more complex. And I'm trying to, I think that they could be ranged by the order of negative impact they have on our program. So we already discussed algorithms. That's how we started. We discussed static methods. We discussed getters, setters, these ER classes. And last time we talked about, do you remember what was the last one? What? Nulls, that's right, exactly, null references. So today we will talk about reflection. Maybe some of you know what it is, maybe some of you don't. Who knows what is reflection? Reflection API in Java. Okay, good. So I will introduce it to you and then explain why it's a bad thing to have in object-oriented programming. So this is the structure of the lecture. We will discuss first typecasting. Maybe typecasting you know, when you switch from one type to another type. Then we'll talk factory methods, class path scanning, annotations, and finally, the philosophical point, discrimination by type. So I will first try to explain you the technical things, why this reflection is technically not so good for your programs. And in the end, the final touch, why it's conceptually, philosophically speaking, is not a good idea. So let's start from typecasting. What is typecasting? Take a look at the piece of code on the left and then piece of code on the right. I am here accepting items and looking at the left code, on the left piece of code right now. I'm accepting items and I'm trying to calculate the size of this iterable of items. Who of you work with Java know that this is the type, the interface iterable, which allows you to go through the sequence of elements. And you don't know the size of this sequence, so it could be endless. So you can go one by one, next, iterate it, like iterators in many other languages. And now, in order to calculate the size of this iterable, I'm doing this, I'm checking the type of the variable items which is coming to me. And if these items is an instance of collection, and collection is, if you imagine the types on the type hierarchy, then you will see that iterable stays here, and collection is a subclass of iterable. So iterable quite simple. It only can go next, but collection is more powerful. It has a few other methods, but it has one additional method, which is called size. So for example, let's say it's a very practical application of this. Let's say you have a database, and in the database you have a huge table, like a very long, a billion items there. And then in Java you want to have an abstraction which represents this long table in the database, and you want to have it in front of you, and you want to go one by one, item by item. So you create this iterable, and iterable only has one method, next. So give me next, give me next, give me next. But you cannot jump to the item number 7 million, or you cannot jump to item number 15. You can only go one by one. In a collection, you can ask the collection, okay, what is your total size? And in this case, the collection will tell you, I have 7 billion or whatever. And from collection, you can extend collection from another type, which is in Java is list. And in the list, you can say, okay, give me the item number 700. So iterable is the least powerful. The collection is a bit more powerful because it has a size method. And list is the most powerful. In list you can jump to any place in the collection. So it depends on your database implementation. For example, if you have a table, a specific one table, then maybe you can use list, because in this case you can jump to any element. But imagine you have a SQL request. So it's a query. So please select, and then many conditions in the select, and you cannot in this select jump to certain elements. So in this case you have an iterable. So long story short, something is coming to me here, and I want to try to calculate the size of it. So what I'm doing, I'm saying, okay, if you are a collection, you who is coming to me. If you are this guy, then okay, I'm lucky, so I'm going to use your method size. So I will do the downcasting here. So this is downcasting. So basically I take the items and I say to Java, I say, I'm sure that this is a collection. It's not a iterable anymore, it's a collection. So I downcast from items to collection. So I was here and I downcast to here. So I say to the compiler, I say, okay, treat these items as a collection now. And there is a method size. And then I call this method size. So I cannot call this size here. I cannot call size right there. I cannot say items.size. If I write it like this over here, it's going to be compile time error. So the compiler will complain. It will say there is no size in there because it is iterable. But since I do downcasting, then size magically starts to work. And I get this size and return. And there's else here coming. The else says, okay, no, it's not a collection. So it's something coming to me that doesn't have the size method there. So what do? I just do the loop. So I'm going to go one by one. Let's say there's 7 billion there. So I will do 7 billion times. Go next, next, next. Imagine how slow this is going to be, right? So this method is actually doing a good thing. So it says, okay, I'm prepared for more powerful things coming to me. And if I see that something is a collection, then I will downcast and boom, use something which is available there. And it looks like a good idea, but it is wrong, in my opinion, how I understand it. And I will explain you why. What is better? This is right. It's better to have two methods. 1, 2. And in Java it's possible. It is called method overloading. Maybe you know this term. Method overloading. It means you have one method name, but you overload it with multiple implementations. That's why it's called overloading. So there's too much, you put too much on one name. And look, indeed the name is the same. Size of, size of. But the parameters are different. In this case, it's iterable. In this case, it's a collection. If you implement it like this, with two different methods, then the client will say, I don't know, the client will do, just say size of, and then provide some ABC, I don't know, something that the client has. And the compiler will see this and will say, I understand that ABC is a collection, so let's connect it to this method. But in some other place where you say size of, and then some X, then the compiler will see that X is actually not a collection. So in this case, we're going to connect it to here. So the decision will be made by the compiler, not in runtime. Here we make the decision in runtime. Something is coming to us, and we check the type, we do downcasting, then we make a decision. Why this one is better than this one? This is the main question. Why I don't like this idea at all. Because it is implicit. Well, we discussed already the coupling. You know, the idea of coupling, it means that if one piece of code knows too much about another piece of code, then they are coupled together too much. And this is bad. So the less I know about you, the better. The less one class knows about you, another class, the better for us. Because you can change your implementation tomorrow, and I'm still going to continue working with you. You don't need to tell me and many other clients that you changed your internal implementation. So the thinner the interface between us, the less I know about you, the better. In this case, the coupling is not even explicit, but I call it implicit coupling. So in this case, look at the code on the right. Here we do, I do one implementation. Well, this is in this case, look, it's iterable. In this case, it's collection. So I provide either book 1 or book 2 to the same method. But for some reason, I will see it. If I compile it, and this is your code, I will see that this one magically works faster. I don't know why. It will just magically work faster. In order to understand why it works faster, I will go into your code, I will see what you're doing, I will say, aha, so these guys, they like the collection better. So I will provide the collection. So I will make an assumption about your behavior. I will implement my code with this assumption in mind and we'll go on. Tomorrow, you will change this implementation. You will do something else. But my assumption stays the same. I still remember, because I learned that 1 year ago, that collection is better for you than iterable. And I implemented my code with this assumption in mind. You didn't tell me that because your documentation doesn't say anything. Your documentation says, give me iterable and I will give you the result. I will calculate the size of it. But something inside your code actually has some extra information, which I retrieved from you. I coupled with this information, so I rely on this information, but it's implicit relying. It's not even in documentation. So tomorrow when you change that, my code will stop working, or it will work completely different. Let's say you change your implementation and now it's vice versa. Now iterable is faster, but collection is slower. So I will open this code and that will be difficult for me to understand what to change. Again, I will need to go into your code and again understand how it works. So you hide you hide important information, and I need to rely on this information even though it's not explicit. And that's bad. That's not good. Everything that's implicit is not good in general. Everything should be explicit. That's my understanding of good design. So if everything is explicit, if everything is visible, if everything is clear to me by looking at the code, if nothing happens behind the scene, then it's a good design. But if something happens, I don't know why, some magic happens, magically something works, it's not a good design. We're just asking for trouble. And this is exactly what's happening here. For some reason, which is deep inside these methods, hidden from me, but okay, of course, in this example, it's easy because it's a method of 5 lines. But people use it not like this. It's just a primitive example for you. But when people do this, when they say if instance of, and then according to this information, they use some, they downcast, and then they use the features provided by the type, which is in the hierarchy, which is lower, then it's a trouble, which I just explained to you, but on a larger scale. In this particular example, it's not so fatal. But imagine you're going to have, hundreds of lines of code where all this instance of is there. So in different languages, that could be different. So in Java, it's instance of. In C#, it's just is. In other languages, it's type of, for example. And I think in JavaScript, it's type of, something like that. So this type checking and then downcasting. This is a very typical pattern when they do type checking, and then if the type is, so something is coming here, which is on top of the hierarchy, and they're saying, maybe you're one of these. Maybe you're somewhere below in the hierarchy. And if yes, then I will use this information. Good. It's not good. Don't do it. What is given to you, that's it. Don't try to make an assumption, or maybe it's something else. Maybe they have some other methods. No. What you're asking is iterable. That's it. Rely on this information. Nothing else is there. Don't try to downcast through the hierarchy of types. Java 16, my favorite language, actually doesn't agree with me, and they even made this downcasting even more convenient for programmers. So it was wrong in Java 11. We were doing like this in Java 11. I just showed it to you. In Java 16, we can do this. Look. You say if items instance of collection, and then you put here like this. So you put C, and this C or X, whatever you put there, ABC, any variable name. So this ABC becomes an object of type collection. So it's just syntax sugar. So they just simplified the syntax. So now instead of writing this downcasting here, you just say if instance of collection, then you put the name, some variable there, and this variable becomes available here in this block of code, and it is of the type collection. So these guys, instead of fighting with this, in my opinion, wrong design behavior, wrong design habit, they just made it even more convenient for programmers. Not good. Try to stay away from that. Not from Java, but from this downcasting. And the downcasting exists in other languages, and it is not only downcasting, but this matching of the matching by the type, and it is called pattern matching. This is the name which you can meet in other languages. First of all, let's see the C#. Look, in C#, they have this, which Java just introduced in the version 16. In C#, as I understand, I'm not a C# programmer, but as I understand, they had it before. So in C# you can write if items is, instead of instance of, you say is. If it is a list, then list, and then list.count. So in this guy, there is no .count. In this guy, yes, the count is available. So you downcast and return. Otherwise, like we did before, you count them one by one. Like we discussed, it's not a good idea. In C# it exists. There is pattern matching in other languages, mostly functional languages, which is very popular. In Rust, for example. If some of you is using Rust, then you definitely know it's super popular in Rust. Let's take a look in this code, what they're doing. This is a type. They declare a type color, and color it's a I don't know if that's the right word, not the aggregation, but there are basically two types inside one. So it could be either RGB with 2 bytes, this is byte, this is byte, this is byte, or it can be transparent. So I can say, look at this, I can say let C is the variable, and then I say color RGB, and then 3 numbers, 1, 2, 3. So this, I create an instance of this type. Or I can create like this, let, I don't know, not C, but D equals to color transparent. In this case, 3 bytes will be encapsulated. In this case, nothing will be encapsulated. So basically, it's like an aggregator of 2 possible types. You can put their RGB type, or you can the instance of RGB type, or the instance of transparent type. And later, in this code, look, the function paint, the parameter of type color is coming in, and we do this match C, and there are 2 situations, situation number 1, situation number 2, the case number 1, case number 2. In this case, we check whether it's RGB, and this is the variable, variable. And if this is true, then this could be like this. So this is the block of code, and in this block of code, we do print, and inside print, we use the variables RGB. Another case, if this doesn't match, then this maybe will match, and we say color transparent. If it's transparent, then we do println. In this case, you see there are no brackets because transparent has no data. So according to the information about the type of the incoming variable, so they're basically doing the same we're doing in Java. They just check if C is instance of RGB, then do this. Otherwise, if C is instance of transparent, then do something else. So they do instance of, they check the type, and according to the information about the type, they redirect the execution into different directions. And this is super popular in Rust. They use it everywhere, this type matching. And in my opinion, this is not object-oriented programming. It's something else. Because in this case, I said here, which contradicts the principle of encapsulation. In this case, to us, the color is coming. The color is the type. It's coming to us. And we, instead of trusting this variable and saying, okay, please print, and inside, you decide how you print. Are you RGB? Are you transparent? It's up to you. So we trust you. We don't want to do your job, because now we're doing your job. Now we're checking, okay, who are you? And then depending on that, we do the printing. But instead, it should be not this way. It should be C.print. And then C internally somehow decides whether I'm RGB, whether I'm transparent, or whatever. But here we kind of deal with this C not as it is an object, but more like just a structure of data with the type assigned to it. So we just treat, basically this is what Rust is doing. It just treats data plus type And type is just information the same as data. So something is coming to us and we're saying, okay, wait a second about the data. First, let me check what is the type. And according to the type, we will redirect the execution. We will go this way or that way according to the type information. And that's kind of wrong because we separate the object into parts. One part is data, another part is type. It shouldn't be like this. For us, object should be something unbreakable, something not, something that we cannot tear apart and deal with these parts separately. It should be one solid piece of something. So Rust, Kotlin, Scala, Haskell, Elixir, Swift, F#, Erlang. Well, I'm not sure about Swift. I think Swift is doing something like this. I'm not sure. But these guys who are, again about Kotlin, I'm also not sure. But Scala, Haskell, Elixir, these guys are functional programming languages, and they definitely have something like Rust has. So they just separate the information about the type from the object. It's like something which is attached to the object. It's like a marker, like a label attached to the object. The object is coming to me, and I'm saying, okay, what's your label? Let me deal with you differently according to the label which is attached to you. It shouldn't be like this. We should not allow our code to even look at this label. We just look at the object and say, work for me, and who are you, and what is your label? It doesn't matter for us. But if we start checking the type, then we, like I said before, we make an implicit coupling with the information about the object. Because look, if this is the code we have here, and then tomorrow I decide to change my color type. Let's say I have RGB here, I have transparent, and I want to add SMYK, for example. You know this format for color representation. So I add this one there, and there are 4 numbers there. U8, U8 is going to be not 3, but 4 elements there. So I extend my type color, it becomes different. So what will it lead to? All the pieces of code which were expecting my type to have only 2 options will need to be changed. So I will need to go through all of the code places and again think, what do they mean there? So the semantic about the object, the meaning of the behavior of the object, is spread over the entire code base. So there is no encapsulation anymore. Encapsulation means I only know about about myself, nobody else. So what happens inside me, only my concern. You only talk to me through my methods. So you come to me, this is the method, you call it, I return you the result. But you don't know what's inside. Here, we obviously know what's inside. We know that there's transparent and RGB, and this is the data, so we know too much. Coupling, that's the problem. So we are tightly coupled with this color type. What it leads to, unmaintainable code. And remember, I told you maybe a few lectures before that all about all these discussions of object-oriented programming. It has one practical implication. We try to improve maintainability. We try to make our programs easily to edit. So it should be easy to edit. If my color type is this, and I have, let's say, 50 blocks of code which do this, which match. So there are 50 places which I need to change when I change just one color, just one type color. 50, it's good if it's one program, but imagine you design a library. Then there are many clients who rely on your library, and then it becomes a mess. You should know, the object-oriented programming is invented in order to get rid of the mess. And by doing that, by allowing people to downcast, even to read the type of an object. In my opinion, this information should be completely hidden. So the information about the type should not be available to the programmer. So I am the object, take me, but you don't know you don't know what is my type. That's, I think, the proper object-oriented programming. When you don't have an ability on the language to ask, what is your type? But in all programming languages, we have that. In JavaScript, we can say type of. In Java, we can say get class. In all object-oriented programming languages, or maybe most of them, it is possible. And when it's possible, it's we just open the window, the door, to unmaintainable code, because the people start coupling. They read the information and they rely on this information. They don't only read, they rely, and we will see how. Okay, so that's all about casting. That's all I wanted to say, that in my opinion, typecasting is bad. Don't do it. Factory methods. And this is part of the reflection idea in general. So I call this lecture reflection because it's all about getting information, like meta information about the object, meta information. In Java, it's called reflection API. In some other languages could be another name, but here let's call it reflection. So we just discussed now that casting is part of reflection because I know this meta information about the object. Factory methods. It's a very, very popular design pattern, factory methods. In Java, maybe it's in classic Java code, this is #1 design pattern. There are even memes and jokes about that, saying that Java, if you can Google that, Java joke factory methods. They will show you that Java is all about factories, factory about factory, factory of factories, factories of factory of factories, and all that. So factory method is basically something like that. Look, this is the more or less classic factory method. Imagine we have an interface figure, and I have 3 implementations of the interface: square, triangle, and polygon. So square is square, triangle is triangle, and polygon is, I don't know, something like with multiple, something like that. So maybe polygon is not a random one, but let's say with the 5. Yeah, I can do that. Okay, so here's the factory of figures, or in Java world they would probably prefer to name it figures factory, but I don't like it. So factory of figures is better. So what do I do here? I say make. So how do I use this? I say new factory of figures, and then I say make, and I pass here 4, and then I say figure f equals to this. So what happens? First I create the factory, and then I ask this factory to make me a figure. You see the type stays here. So I don't know what will be returned from there. A triangle or polygon or square. It depends on the implementation of the method make. So the method make will take the number of sides. So how many sides do I need? If I need 3 sides, it will return me the triangle. If I need 4 sides, it will return me the square. Otherwise, it will return me the polygon. This is called factory method. It is convenient. Some programmers may say it's convenient. So instead of doing this if everywhere in the code, they just say I just make one factory, and every time I need a figure, and I don't know which one, so I don't need to know that you have square, you have triangle, you have polygon. So they say, let's say for example, you introduce octagon for 8 sides. So then I will need to go through all my code and implement this if in my code as well. I don't want to do that. I just want my factory to become smarter, and I will just inject here new if sides equals to 8, then octagon. It's convenient, right? So the factory knows everything about how to create this figure, how to create this shape or whatever. However, I think it's not good. This left code is not good. The code on the right is better. Let's see how the code on the right works, and then we'll discuss why it's better. Here I get rid of the factory entirely, so there is no factory. Instead, I make a class which is called polymorphic figure, and it also, that's a typo, implements a figure, and this is the method which is everywhere. You see the surface method, it's from the interface, and inside this method I make those guys and I redirect the call to their method's surface. So I don't let the client make different objects. I instead say that there is an object which already encapsulates the functionality of making the right decision of how to calculate the surface of a polygon. So here, this code will look like this. On the right side, the code will look like this. New polymorphic figure. This is my class. And then I say for, and that's it. Figure f equals. So on this code, first I make a factory, then I say make. On the right code, I just make an object. And the mechanism of making different implementations, of finding these different implementations, of finding which one are suitable, is encapsulated inside the object I just created. This, I think, is more elegant. Because I'm trying to, I have an intuition that it's better. I'm trying to explain in words. So I said here that the semantic of object construction is not visible to the client in this case here. So the client doesn't understand that we're going to have three implementations, that we may have different implementations. So the coupling is loose, which is better. So this is good. Loose coupling is better. Tight coupling is bad. So in this case, when you do it like this, then you don't expose to the client the mechanics of making an object. Because here the client knows, well, there's a factory, so it means that there are different implementations. Okay, I understand there are different implementations. How many of them? I don't know, but I can click there and see how many implementations. I know too much. And then I say, okay, so first I make a factory, and then from this factory I do make, so they return me the proper implementation. So the client understands there is two-step mechanism that you're going first, they're doing some search, some finding the right implementation, and then you return it to me, and only then I can use it. Here, it doesn't look like this to me. It just looks, hey, I have a figure. I have a figure which has 4 sides, and what's going on inside, I don't care. Which is better. The less I know, the better. It's kind of intuitive, yeah.
So does it mean that whenever we want to add functionality to the interface of figure, for example, we have to change both classes? So classes of polymorphic figure to add the functionality of explicitly making new call to function that we have just created, instantiated in the figure interface, and also making it in the interface itself.
Yeah, that's right. Yeah, we will have to change, but it's going to happen everywhere as well. So if you change something in this interface here, if you change this interface, you will have to change these 3 guys and this one. So in 4 places they will have to make changes. Here you make changes only in 3 places. You're right. On the left example, if you change, then there are 3 places you will change there, and this one will not be changed. Because it will stay the same, you just return the object, you don't change the implementation. But in this case, I think it's good, because we hide more. So instead of doing 2-step interaction, we do 1-step interaction. The more we hide from the client, the better. The less the client sees about us, the less the client understands how we work inside internally, the better. Because the less the client knows, the less assumptions the client will make.
But in case we want to access the whole object, like we want to get a instantiated class of square, for example.
Then just go, if you want to just square, then just make new square. So you don't need factory for this. Yeah. So factory is kind of, the factory, they're trying to abstract some mechanism of decision making. So the number is coming, it's 1, 2, 3, 4, 5, and according to the number we make a decision, which class to instantiate. And this is some mechanics. In this case it's very simple, primitive. Sometimes it may be more complex. They make more complex decisions. And this decision-making mechanism, in my opinion, should be hidden. It's very subjective. So in this case, don't take me as a complete truth. Think about it. But this one is definitely true. So I'm giving you another example how the reflection is being used, generating class name from a string. Take a look at the code. Again, factory of figures, but now the name is coming here, not this number of sides, but the text, the string. And the text may be, let's say, we call it like this. I say new factory of figures, and then I say make, and here I will say square. So it will come in here, the text, and then in Java we use class for name and then the name there. So this is pure reflection API. So Java will just, using the name as a string, the Java will go to Java Virtual Machine pool of all the available classes. It will find in this pool of available classes the class by this name, which is going to be this one, and then it returns the special object called class in Java, which you can do like this. You can say get constructor, so you take from this class a default constructor, and then you make new instance from this constructor, and finally you return the figure. So this is a more abusive, in my opinion, example, a more abusive way of using the reflection API, and this is more typical for factory patterns. So these factory patterns, usually they work like this. You provide the string, and then this string, they somehow convert to a name of a class. And that's bad. I'll explain you why, but let me show first what is better. So this would be better. Again, we encapsulate it all inside some special class, forget the factory. And in this special class, which is, again, my typo, so it implements the figure. And in this polymorphic figure, we have the method surface. Again, that should be override there, override before the method. And then we say if the name equals to triangle, then we return the triangle. If name equals to square, then we return square. Otherwise, we do polygon and then, I don't know, some calculation of the numbers. That's a different story. So we, instead of using this mechanism, we more explicitly compare the string with what's available, and then we go to the operator new. So here we don't have the operator new at all. We have this method, new instance, which goes through Java reflection mechanism, but here we have normal new operator. So I am always in favor of a new operator, because new operator, like it says here, no surprises expected. New operator is explicit. Again, explicitity is better. It is an explicit mechanism of making an object. This one is not explicit, it's less explicit. So when you do it like this, class for name, many things may happen on this call or on that call. Many unpredictable, many unexpected things may happen. If I provide, for example, in this, I say make, and then I provide, I don't know, hello world. What will happen? Many things may happen. First of all, of course, maybe the exception will be there. It will say, okay, there is no class with the name hello world. Maybe. What if I provide there, I don't know, the text string? Will it find the class string? Probably it will, because string class exists in Java. Will it get the default constructor? I don't know. Maybe. Probably yes. Maybe not. And then will it get the make a new instance? Probably not, because of many reasons. So many unexpected things may happen in this code, and which is bad for maintainability. We don't want to have something which is not clear and obvious when we look at it. Here it's absolutely obvious. We just compare the string and we do new triangle. We compare the string, we do new square. We compare, we do new. It's very easy to create a unit test for this code. It's very easy to understand how it will behave. This is reflection API. It leads to, it's called reflection API in Java. It leads to tons of different problems which are sometimes very hard to pinpoint and understand where they are. So I believe that this generating class name from a string is in general a bad habit, even though it exists massively in Java everywhere. Okay, so if you can stay away from that, it would be good. Sometimes you will see that people use it because they just cannot write the code like this, because it may look difficult for them. Sometimes they may tell you sometimes that we don't know in compile time, we don't know when we write the code exactly what classes will be available. They will tell you that, look, this is more flexible, this mechanism, because anything can be provided here, any name,
And let's say today you have 3 classes, but tomorrow you're going to add class number 4, class octagon. We don't need to change this code, right? It will just work. Just call it make octagon, and the code just remains the same. Just change the code of the client, and the code of the provider of this one, it will remain the same. It is true, that's right. But at the same time, it introduces unexpected behavior, because what happens if by mistake I provide the wrong name? What happens if instead of octagon I see too many classes which just show up there, become available, and I don't know exactly what I'm calling. Whether I'm getting the right class or I'm getting something by mistake. And in Java, this protocol is aggressively used. This mechanism of this dynamic loading of the classes very actively used in the in so-called service provider interface, where they provide you the factory where you can. They provide you the library. They provide you the library. In the library, they give you the method, which is called not make, but let's say make. Let's say calculator. So you have the make me the calculator, and this make calculator doesn't know which calculator to return. So when they create the service provider interface, the SPI, they don't know exactly which calculator to make. What is the object to make? And there should be another library, which they sometimes call the implementation or runtime. And this library, another jar file, another block of code, actually has the calculator. And they go together. This and this, you put them together into your software. And then you call here, and this guy starts searching where is the right implementation. It finds the right implementation and returns it back to you. So there are two guys playing together. This is like an interface which doesn't know what's going to be the implementation, and then the implementation is located nearby, and somehow they get connected. And usually they get connected through this interface, through this reflection API. So the interface is looking for implementation, and when it's found, it's being returned. So many hours of debugging I personally spent on this, because it's very hard to understand why it doesn't find the implementation, why it finds the wrong implementation, why it doesn't find anything, or why it finds two implementations. It's just hours and hours of debugging. It's very typical a Java-related problem. When the SPI, the interface, is available, but when you call make me, okay, give me the implementation, they just start looking everywhere, and there could be tons of problems in there. And you cannot click there and understand, because when you click the make calculator, you end up in the code like this. There is some magic. Just go and look for the class by the name. Where to look, how to look, where it's going to be located. No idea. It could depend on many factors, on Java virtual machine, on the location of these jar files, on the dependencies, on many things, which you don't know when you look at the code. If the code would be like this, I just click at the method, I just see, okay, there's a new. So I click at this triangle and I open the class. Just one click of a mouse. I just go down, and my code becomes clickable through, I would say. So I can click through the code into deeper and deeper level down to the implementation. In this code, I cannot click anywhere. That's it. It's like a black hole for me. For name, what do I click? There's nothing to click. We'll just stop right there. What will happen there depends on runtime situation. And that's not good. So implicit things in your code are bad. Explicit are good. Next chapter is class path scanning. Again, this is where reflection is being used, and again, it's a bad idea, I believe. Let's see Java example. So look at the code on the left. Let's say we have an interface foo, and we have a class bar which implements foo. Then there is a library. I use the library called reflections, very popular in Java for this specific purpose. I make reflections, new reflections. Here is just an empty string, which means look on the entire class path. Class path is in Java, maybe some of you know, it's just a place or many places where Java Virtual Machine is trying to find your binary files, binary classes. Class path could be a number of directories, a number of jar files, so it's just a collection of places where to look. And if you say empty string here, it means that this library will just go through all of the places. It will just try to look in every place. And then look what happens here. I'm saying this RTS, I just created this object RTS, so I'm asking this library, I say get, just the method, the main magic method, and I provide the request. The request is this, subtypes of foo class. Just don't pay attention how it's formulated, just this is how the library works. What's important is what's going to be, what it's going to do. When I do this, it will go through all the available files in class path. There's 100 of them, 1,000 of them, 1 million of them, doesn't matter. It will go through all of them one by one, and we'll try to find every class which implements foo. It could be quite convenient. It could be quite convenient. Sometimes it may look like convenient. For example, I can give you an example where people use this. So let's say you you have the interface foo, but not foo. Let's say you have figure, like we had in previous examples, figure. And then you are trying to, so you make a software, and then you have a team of programmers, and you said to all of your programmers, implement different figures, octagon, polygon, rectangle, circle, everything. Just do different things. And you have multiple programmers who contribute to you. One guy did something, another team did something else. So they put everything into the libraries. And then in one place, somewhere here, you want to have a list of all possible types which implement figure in order to, let's say, give the user the possibility to choose in the drop-down select box, like which element to put on the graph. So you need to somehow go through the entire code and find who of these classes implement your figure interface. How do you do that? You use this reflection library. It will go through the entire collection of all classes and find you what you have. It seems to be convenient, but I think it leads to disorganized, chaotic structure of the code. Because, again, the link between the place where we need them and the place where they live is not explicit. So there is some magic called reflection library, which will magically go through all locations and find for us what we're looking for. And this magic is unclickable. So I cannot click anywhere and see while I'm looking at my code, and I cannot see what is there, what are these classes that implement the interface I provide. So instead of doing this, it's better to do, like I said here, use explicit object instantiation. So just everywhere, just in this case, in this particular case, you need to know what are the implementations. So ask the programmers, go through all the libraries and put them in the list right here. In this case, the link from the place where you use them and the place where they are declared will be explicit. It will be clickable. And the same people use for annotations. Maybe you know in Java they have annotations. So let's say this is the interface for the annotation called foo. And you can put it like this, attach it to a class. So you define your class bar and then you put the annotation on top. And this class is called annotated class, which is sometimes may be convenient. Again, you design different classes, you put these markers, these labels for them, annotations, and in some central place you just say, hey, give me all the types which are annotated with my foo annotation. So go through the entire class path and find me all the classes which are annotated. The library will do the magic for you, definitely. But again, in my opinion, that's a bad idea because you don't know how it will happen. Magic will happen inside. Of course, you can say that you understand how it will happen. You understand the mechanics of this of this reflections library. That's all true. But maybe on a simple example, it will be true. But if you abuse this, like, for example, Spring Framework, they do it a lot. In Spring Framework, a lot of things just happen through the annotation. So you just annotate your classes, and then magically, boom, they just start being discovered. So you just run your Spring application, and annotation is there, application is here, and they just, boom, magically got connected for some reason. That's if you're really professional about the library, you will probably understand why. But otherwise, it will be absolutely for you look like magic. So reflection, finding in the class path, I think it's a bad idea. Let's talk about annotations in general, because annotations cannot live without reflection. Reflection API just goes hand in hand with annotations. Reflections API. They just go together, annotations. In Java, annotations, maybe in other languages they also exist. So let's say you have, I will show you a few examples where annotations can be used and where I think they are okay or more or less okay, but again, it's better to not do this, but at least it does make sense, sort of. So let's say, for example, in this, look at this code. We have an interface called pub, means publication, so some paper, some publication, and the publication has the ISBN number. So I define book and I define journal. The book is a publication, the journal is a publication. The book overrides the method ISBN, so it will return some number, and the journal returns some number, ISBN. That's okay, that's so far so good. But now we define static methods. Look at this static method. You know, static is bad, but still. So we attach to the book, we say that your category is book. So basically, for all books, for all instances of this class book, we say that they will have a category, and the category will be book. And for all instances of a journal, we also have a category, and the category will be journal. So where do I put this information? Static methods, it's very unelegant. So we talked about this. A static method looks pretty ugly. But where do I put the information about the book? I can make this method not public. But in this case, every book will have the same constant returned here. Because for all books, the method category will return book. Book, everywhere. So it is actually static, because it is not going to use any internal attributes of the book, of the class book. It will always return a constant. So it looks like a static method, but static is a sin. So I think a better design in this case is to use annotations. So look, we still have the same interface pub, we still have the same method ISBN, but then we define the annotation, a so-called, it's runtime annotation, I think it's called retention policy source. So the point is that this annotation, this is the definition of the annotation. We just define that annotation is possible, and then we use this annotation here. So look, in the class book we have annotation, and in the class journal we also have annotation. So we attach some information, some marker to the class. So all books. So when the book comes to me, I can use Reflection API and ask Java virtual machine, what is the value of annotation category which is attached to the book you just sent me? So I will do this. Let's say this is the book, B is coming to me. So I will do this, B get class, and then get annotation. And then here I will say category, class, and then from here I will say dot value. So this is how I will, and this is going to be book B. So for me the B will come, I will take this B and I will say get me the class, it will return me either this or that, and then from there I will say, it's not even book, it's going to be pub, sorry. It's going to be publication. And then get class. So here will be returned, for example, class book. From here, I take get annotation, category class. So from here will be returned the instance of this guy. And from there, I call value, dot value. So it's like a meta information which is attached to a class. It's, in my opinion, this whole thing is ugly, but it's better than static methods. So it could make sense to use, well, I do it sometimes. Do it like this. When I have multiple objects and I know that these objects, they belong to different classes, maybe a few of them, and I understand that there should be some markers potentially attached to different classes, and I want these markers to be class level markers, not object level markers. In this case, annotations plus reflection API, because this is completely, this is reflection, this is reflection. This get class, get annotation. So I'm getting meta information about the object. I'm not talking to the object now. Look, the publication came to me here, pub, and I completely ignore all the metas. I'm just saying, get me the class. So I'm taking the, I'm getting the metadata from that. That's very, very hurtful to the object-oriented nature of this guy, because it was unexpected. I'm the object, I'm trying to protect myself, I'm trying to encapsulate everything, and then they're just like, hey, boom, give me your class, and then from this class, give me your annotations, and then give me the value. That's completely out of my control, because the object doesn't know anything about what happens. This happens, this happens, this happens. It's completely outside of control of the poor object B, which is absolutely, even doesn't know that this happens. But this is Java design. Another example of annotations is locating methods. So we discussed this API for the RESTful interfaces on the previous, or maybe a few lectures ago, and I told you that these controllers, people use annotations in order to inform the controller. This is going to be extends control, I think, the abstract controller or something. Abstract controller, which will work like this. We want this controller to see which method to call. So the controller, the request is coming to the controller. The request says, I don't know, slash hi. And this is the name of the request. So the controller needs to understand which method to choose. And this could be many of them: string title, string name, many entry points. And the controller needs to decide which one to choose, And this decision needs to be made, it is made, using the annotations. And this is how it works. Let's say it's a new books controller, and we take, again, the class information. We take information about the class. Then we say, give me the list of your declared methods. So you see what happens. So just give me the names of your declared methods. It's absolutely anti-object-oriented approach. And then we say, for each method, we ask, is annotation present? So do you have this annotation pass? And if the annotation is there, we say, get me the annotation. And then from the annotation, we take the URL. So this is the URL. So these guys get the class, get declared methods, is annotation present, get annotation. All of this is called reflection API. Reflection API. We take meta information about the object while the object lose control right there, right here. You see, it's book controller. So the object doesn't know what's going on, but this algorithm, this procedure, knows way more than the poor object. So that's bad. To try to find a way not to do this. We don't have time to discuss how to do it differently, but just remember that when you see things like this, then you know that you are far away from object-oriented programming. You do something else. You do something. You treat your objects now not like objects, but like something else. The control is not anymore in the hands of your objects. Okay? What else? Yeah, now it's a very interesting topic. It's called dependency injection containers. We discussed that before a little bit, and now I will dig a little bit deeper into this topic. Dependency injection container. Look at this code. It's very popular paradigm, programming design pattern, which is used in many frameworks these days. And in my opinion, it's a bad idea. It's a very dangerous design approach. Look, this is the shopping cart, and we have some shipment interface. Shipment is some interface which we can have, maybe somebody will implement this interface and implement the method cost. So I can ask this object and say, what is the cost of shipment these days? So how much will it cost to ship the book? And the answer will be like $5 today, $7 tomorrow. So it's, let's say it's some active component which knows how much is the shipment. So we just calculate the cost of shipment. Now we have a shopping cart. The shopping cart has the private attribute shipment, and it has the book. So the shopping cart basically has a book, and somehow it needs the shipment to calculate together what is the cost of a shopping cart. So into the shopping cart we can set book, which is also ugly way to, because the seller, we discussed that, but this whole code is ugly, so just look at it and assume that this is the code you see in some software which somebody else created. So how the cost is being calculated? You say book.price, encapsulated book, you get the price, good. And then you go to encapsulated shipment, get the cost, and then summarize them and return. So far so good, but the interesting part is this, the annotation, inject. What does it mean? Look how it works. It's called dependency injection container. First, you create a container, some magic container provided to you by a framework. Usually it's implemented by somebody else. You don't implement it yourself, you just get it somewhere. And then you say container make, and you provide the name of the class, cart. It will create an instance of this cart, and it will see that you have the inject annotation there, and it will set something here. So you will get the cart, but not empty, not null, because here it will be null. The book will be null. But here, the null will be replaced, the container will replace it by the implementation of the shipment. So the container will go around your program everywhere, will try to find the implementation of the interface shipment, will make an instance of it, and set it here instead of null. So it's kind of convenient. It may look convenient because you don't need, first of all, you don't need to remember where is the implementation of the shipment. You just magically set inject, and wherever it is, it will be found. So you can implement shipment here, you can create a cart there, and then in the container you say make me the cart. And the container will just find the shipment magically somewhere in the class path and make it and inject into you. And there could be many things like this. Database pool of connections, the storage of the files, the connection to the net, the many things which you don't want to remember where they are. You just mark them properly with the annotations, and your dependency injection container will just magically find them everywhere, and every time you use inject, it will just inject it there. So the code will look like this: container make the class, then you set book, and then you call cost, and it will work. If you look at this code later, you will ask yourself, where did the shipment came from? I didn't set it. I set the book, but it works. So who set the shipment? Then you will go there and say, there's inject annotation. But still, the question remains, what is the shipment? I don't know. It's just somewhere. Where? Just somewhere. Some people may say it's good, it's magic, they love it, because it's somewhere. I don't need to think about it. When I talk about this at some conferences, people usually tell me like, it's good. So why are you complaining about this? You don't need to remember. That's what we were fighting for so many years. And now you're telling us it's bad. So do you want to remember where is the shipment? And I'm telling them, yes, I want to remember. I want to have here another method, set shipment. And then in the set shipment, I will have some parameter which is clickable. And I know exactly what is the shipment. I know exactly what I set in there, what I injected there. Again, remember this setters, it's ugly, but still, this is not the discussion here. But people who will argue in favor of dependency injection container, they will tell you that this actually is a solution for the problem. I don't think it is. So this is I explained you everything I just told you. I wrote the algorithm, how the container works. So this is how the method make inside the container may work. So first, you say, well, when I say here, I say make cart. So what exactly the container does? First, it finds inject annotated shipment field. Okay, inside the cart, there is a field annotated with annotation. Inject. Okay. Point 2, make an instance of shipment. So it make an instance of shipment, like I told you, finding it somewhere. I said here, how do you think at the step 2, what class will be instantiated? That's a big question. Number 3, it stores it in the cache. So somewhere inside the container, there's a cache. So it's not going to instantiate shipment over and over again. It will do it only once and store it internally. So if you and when you make another cart, then the same shipment will be injected. Well, it's configurable probably in modern dependency injection containers. You can configure that stuff. You can say store it in cache or don't store it in cache or store a number of them in cache. All this stuff is configurable, but by default, it's going to be the same shipment over and over again. It will be just made once. And again, this is what people will tell you. This is the benefit, because you don't need to make singletons. You don't need to worry how to have this shipment only once in your code. Because without dependency injection container, you need to make a shipment and then pass it everywhere. Use it. So it's going to go into every cart. With the dependency injection container, it will be just some magic container which just magically holds the shipment, and every time you make a cart, it will just inject into it. In my opinion, it's bad. It's better to pass it through from place to place, because explicit design is better than implicit. So step number 4, it makes an instance of the cart. Then it stores cart in the cache. So the cart will also go into internal cache of the container, and then assign shipment to the cart and return the cart. That's the whole story of how dependency injection containers work. They're called dependency injection containers, DI, or sometimes DI containers. When you hear that, and you will hear that, know what's going on. Know that some magic starts to happen. How I suggest to get rid of that? How can we do dependency injection without it? So dependency injection by itself, it's a very good idea. Containers, dependency injection containers, is a bad idea. That's my message to you. Dependency injection is perfect. So we want to inject dependencies. We don't want the cart to know about the exact implementation of the shipment. We want the shipment to be injected into the cart. Because without dependency injection, how people designed their code before dependency injection was officially invented, the term dependency injection, people were just doing like this. You need a cart, you create a cart, the cart needs the shipment, so the cart inside makes the new instance of a shipment, or maybe just links to the singleton or whatever. So the cart knew everything. What is necessary for the cart, this information was contained inside the cart. Dependency injection means that the cart doesn't know nothing, and when we make a new cart, we need to provide dependencies. The shipment, the book, the everything. Everything needs to be provided, injected, dependency injection. So you give it into. So this is the design, the same, but now we don't have we still have, look, this is the old implementation with the setter, with the inject annotation, everything, you just saw it, and this is the new implementation. The interface stays the same. The cart, both of them are final. The shipment and the book, they're final. Both of them are coming through the constructor. And then how we can instantiate it, we say new cart, my shipment goes in here, book goes in here, and then we run the evaluation. So instead of having this container, we don't need the container, we just inject our dependencies like this, through the constructor. And we explicitly say my shipment. So this is class that implements the shipment. It is clickable. So I can look at the code, I can click and say my shipment is coming in there. Not some magic which the container will find, but my object. It's quite simple just to remember, don't use containers, and that's it. And you will have to do it this way. You will have to provide dependencies. Or, of course, you can make dependencies like this, equals to new my shipment. But this is bad. This is no dependency injection. Not even no container, but this is no dependency injection. And that's very, we don't do it this way. We don't do it this way now. We did it a long time ago, but now I think everybody understands that this is no good. So people either will use containers, which I'm against, or they will do it like this. They will provide dependencies as arguments to the constructor. But this is absolutely no go. No. Not at all. Everything should come through constructors. Everything that you need should arrive to you through constructors. Ideally, in ideal object-oriented world, the new operator must not be used inside your objects. So your object must be free of new operators. So everything should come to you. You should not, inside the object, should not make new objects. If you need them, they must arrive to you through constructors. So look at your code and think how many times you use new operator. If you use it frequently, then it means that you don't do dependency injection as often as you can, as you could, as it would be good for the design. Okay, and final point. We still have some time. So now philosophical concern. That was more technical things, more practical things, now philosophical concern. So look at the code on the left. We have interface figure. Let's say I have one method rotate, and then I have class circle and class square. So there are two things which if this is the figure, and then this is the circle, and this is the square. So they both are subtypes of the figure, and they introduce, they implement the method rotate, both of them, and this one introduces radius, and this one introduces side. So the square has the side, and the circle has the radius. Two additional parameters, okay? And this is what is polymorphism. This is what a good object-oriented programming looks like. I say, calculate me the surface of the figure. And I do figure surface. So I ask the figure is coming to me, and depending on the, So I don't have the surface method there, but I understand that now I want to calculate the surface. And in order to do this, I will need to introduce this method into the figure. And this is typecasting. In this case, no, I'm just looking at the figure which is coming to me, and I say, if this is the circle, then I'm gonna calculate the, this is wrong, this is multiplied by 3.14 by radius. So there's one formula, this is another formula, and this is the exception. So in this case, I don't treat the object as a self-sufficient entity, which is capable of dealing with itself the way it's necessary. I'm using the word discriminate. So I discriminate the coming entity to me depending on what it is. So if you're coming to me, if you are the circle, then I treat you one way. If you're coming to me, you are the square, I treat you another way. If you're somebody else, I'm going to treat you another way. So instead of just saying, hey, you're coming to me, I need from you this service, so just give it to me. I don't care who you are. I don't care, you circle, you square, whatever. Just give me the surface, just calculate it for me. If you don't know how to calculate, okay, let's go back to you and introduce this method to you. You need to know how to do it. It's like a student coming to the door and I say, I need you to, I don't know, to answer the question for the exam. That's one way. That's object-oriented way. I don't care who is the student. I just care, answer me the question. Are you, I don't know, what is your name? What is your age? I don't care about this. Or a different story. The student comes in and I say, oh, are you younger than 20 years or are you older than 20 years? So I'm going to treat you differently. The younger guys say stay here and I'm going to ask them one type of questions. The older guys stay there and I ask them different questions. That's what we have when we do the typecasting. So I separate people, I separate objects by categories and then I treat them differently by categories. It's just not object-oriented. It shouldn't happen this way. I should just put this responsibility of dealing differently on the shoulders of the object. It's your job to do the job. Just answer me the questions. Just do the work you're supposed to do as a student. But I'm not gonna put you into different categories and then deal differently with categories. Oh, these students, they know how to do this. I do it with them. They can answer that questions. And these students can answer different questions. That's discrimination. And it leads to wrong design. It leads to, again, like in the beginning of the lecture, I told you, I will know too much. I will be, as a teacher, I will know too much about students, that these students can answer these questions, these students cannot answer these questions. I don't want this information. I just want a student in front of me, an object in front of me. And then I ask the object to do the work for me, and the object either can do it or cannot. That's it. But I never try to help the object. I never try to do the work instead of the object. And this typecasting and deciding what is the type of an object, it's anti-object-oriented idea. It's against encapsulation. We must encapsulate. We must not typecasting. Again, I will repeat them. I think in the proper object-oriented world, there should be no types visible. There could be types, but there should be no type retrieval mechanism. Types is okay. You type, you subtype. That's a good practice, definitely, for polymorphism. But when something is coming to me and this is an object, I should not be able to understand what is the type of this creature. No, I only use the methods. I say dot surface, whoever it is. And the compiler will tell me the surface is there, the method exists, or no, the method does not exist there, compile error. That's all right. But when I start asking what it is, when I start asking what is the type, then I make too much, I make the assumptions, wrong assumptions, or maybe now right assumptions, but in the future they will become wrong assumptions about these objects. And they will lead to design degradation. Eventually the design will degrade. Eventually these assumptions, there will be too many of them, and it will be very hard to understand which of them are true, which of them are already false. So we don't make these assumptions. We just look at what's coming, ask to do the work for us, call it a day. That's what I wanted to say about reflection and typecasting. This is a very sensitive topic. If you talk about this to mature programmers in object-oriented world, they will tell you that everything I told you today is completely wrong. Just be prepared for that. So most of, maybe not everything, but most of what I told you, the conventional programmers, traditional programmers, they'll be very much against that. But I try to give you the reasons. I try to explain why we will just asking for trouble if we do a casting. We need to do polymorphism. Polymorphism means what's coming to me can have many forms. Morphism means forms. So there could be many forms. The student can have many forms. I don't know, a tall student, a short student, an old student, a young student, doesn't matter, all different forms, as long as the service is provided, as long as this person can give me what I want. All right, thanks. That's it.